Hello, welcome back to the basic Python course. This is our 10th session today on array computing, in which we will have a look at how to work with vectors and matrices in Python. So a lot of tasks require manipulating numbers, which are organized as vectors or matrices. For example, if you're storing the reaction times from all the trials in a psychological experiments, you'll need a vector for doing this. Or if you are fitting a linear regression model, which is specified by its regressors, you'll need a matrix to store this design matrix of the model. So for the purpose of this session, I will assume some mathematical basics. So I will assume that you have heard of the following topics, that you know what vectors are, what matrices are, that there are row vectors and column vectors, what a scalar is. And then in a few minutes, we will also have a look at matrix multiplication and coordinate rotation, which are based on this knowledge. So this is the matrix, and this is a matrix, or a representative from the family of matrices. So a matrix is just a collection of multiple numbers, which is arranged in rows and columns. Often the rows correspond to single observations. So a single person or a single animal or a single trial from an experiment. And the columns correspond to measurements or to the dimensions of the space in which an observation is placed with those measurements. So for example, here, the first column might represent the age of individual people. Second column could be their height or their IQ. And third column could indicate whether they are a smoker or not. So a single row from this matrix, or also a matrix with just one row, is called a row vector, and this might represent just a single observation. A single column from this matrix, or a matrix with just one column, is also called a column vector. And this might represent a single measurement or a single dimension of the space in which observations are placed with those measurements. Finally, a single entry from a matrix, or also a matrix with just one row and one column, is referred to as a scalar. So a scalar is a real number. And if you have ever done any calculations in your life, you have already worked with matrices because all numbers are one by one matrices. Okay, multiplication and summation of matrices with scalars is easy. We can just multiply each entry of the matrix with a scalar or add the scalar to each entry of the matrix. But multiplication of two matrices is more complicated. So first of all, matrix multiplication only works if the number of columns in the first matrix A is equal to the number of rows in the second matrix B. And then to work out the matrix product, it often helps to write the second matrix on top of the result here and the first matrix to the left of the result. So this entry in the first row and second column of the resulting matrix would then be given by the product of these two vectors. So you take the first row from matrix A, second column from matrix B, and multiply their values element-wise and then add them up. So A11 times B12 plus A12 times B22, the result of this would go into this entry of the new matrix. And if you want to calculate the third column, third row of the resulting matrix, you have to take the third row and third column from the original matrices. So here's an example for that. Let's just check two entries to see whether the calculation was correct. So let's have a look at the 7 here. This should be first column times first row times first column. So 1 times 1 plus 2 times 3. This is 1 plus 6. This is 7. And then let's also have a look at the 34 here. This should be third row times second column. So this is 9 times 2 plus 4 times 4. This is 18 plus 16. This is 34. Okay, so this is how matrix multiplication works. And then in the session today, we want to have a look at coordinate rotation. So take a look at the blue points here. They are all lying on a straight line. And they are characterized by x and y coordinates. For example, the y coordinates of these points are 2, 3, 4, 5 here. And now if you take these points and rotate them by 45 degrees, you end up with the orange points, which are again characterized by x and y coordinates. So the intersection of these two lines, the x and y axis here, is called the origin, the point 0, 0. And what we have mentally done now, we have rotated around the origin. In principle, you can also rotate around other parts. So it turns out that coordinate rotation can be represented in terms of matrix multiplication. So coordinates are given as an n times 2 matrix, meaning they have n rows and 2 columns, where the first column are the x coordinates, the second column are the y coordinates. And if you have a matrix specified in this way, you can multiply it with a 2 by 2 matrix whose entries are given as sines and cosines of an angle, and this will then rotate those coordinates by the specified angle. So what does the 0.79 here stand for? Usually we are giving angles in degrees, so from 0 to 360 degrees, for example. One can also specify angles in radians. So the conversion from degrees to radians is easy. You take the angle in degrees, divide by 180, and multiply with pi. So an angle of 180 degrees would be equivalent to pi, 360 degrees would be equivalent to 2 pi, and so on. So if you have a look at this number, this is pi divided by 4, pi over 4, meaning that the corresponding angle in degrees is 180 degrees divided by 4, which is 45 degrees. So this is actually rotating the coordinates by 45 degrees. Okay, so with that, we want to come to our objective for today. So what we want to reach at the end of today's session. So let's take a rotation of coordinates as an example and see how to implement this. Our goal is then to write a function which rotates a matrix of coordinates. Once again, that's a matrix with a certain number of rows and 2 columns. And the arguments of this function should be, of course, the matrix of coordinates that we want to rotate, and the angle of rotation could be given in degrees. And then the return value of this function should be a new matrix which contains the original coordinates but rotated by this angle. I will then, if we have done this, also show you some basic ingredients for plotting the coordinates. So what we want to have in the result is something that looks like this. So with that, I would like to switch to Spider and start teaching you a bit about representing matrices in Python. So if we were to store information organized as rows and columns into variables, the first try at this could be coming up with nested lists. Yeah. So let's, for example, take our coordinate list or define a variable called coordinate list. And we say that this should be a list of rows. And each entry of the list should be another list containing the entries of a single row. So this is exactly the number. Sorry, this is exactly the coordinates that we were using as an example. I'm here adding 0.0 at the end to enforce all of them to be float variables. And if I have enter, I have my nested list of coordinates, where once again, each entry of the outer list is one row, and the entries of each inner list are the elements in this row. So this would allow us to access individual rows. This, for example, would be the third row. And also to access individual elements. This, for example, would be the second element in the third row. However, lists are not a very good way of storing matrices in Python, and there's a few reasons for this. So the first reason is that matrix operations performed on nested lists would be tedious. So let's say we would like to add a certain value to the first entry in each row, so to the first column essentially. What we would have to do then is like write a loop across the rows, and for each row, yeah, take its first value and add a certain number, let's say 1. I'm sorry. So if we then have a look at our coordinate list, this has worked, but it's very, very complicated to perform just this very simple operation and having to write a for loop for it. Second, nested lists are not constrained to have equal dimensions. So if we were, for example, to take the first row and append a certain number, so add a certain number at the end, this would make our coordinate list valid, but obviously this would not be a valid matrix because in the matrix, all the rows need to have the same number of columns or need to have the same number of entries. And here we would have 3 entries in the first column and 2 entries everywhere else. So we would like to use a data type where this is not possible. Finally, nested lists are not very strict about data types. So we could, for example, come up with the following crazy matrix. And this would be a valid nested list. And we could, just like before, access individual elements from that list. But obviously, this is not a matrix in the mathematical sense, as it contains entities which are not numbers. For example, it has strings and variables of none type in it. So this is a matrix which should also be disallowed if we are working with proper mathematical matrices. So the solution for this is to, instead of defining the matrices ourselves with the data type we already know, to use Numpy, which is short for numerical Python. And Numpy stores everything as arrays. So an array is just a collection of homogeneous values in rows and columns, or even higher dimensions. So potentially with having layers as a third dimension. So for all of the following, I'm going to import NumPy as NP. So I'm using what I earlier referred to as a renamed import, because this will make my commands a bit shorter. And then let's take our coordinate list again, which we defined as a nested list, but this time call NumPy Array with this nested list as an input argument, and write the resulting variable into the name coords or coordinates. Okay. If we print those coordinates now, we have a proper two-dimensional matrix. And the structure is also indicated to us by here using the double square brackets to say that here this is the start of the matrix overall, this is the start of the new row, end of a row, and so on and so forth. Now, matrices always have certain dimensions, and we can access these dimensions by asking the array attribute shape. So if we type the name of a NumPy array and then dot shape, this gives us the number of rows and columns in this NumPy matrix. And here the convention is always to have columns first and rows seconds. This is equivalent to the way in which matrices are also indexed. Now, NumPy obviously does not only allow to create two-dimensional matrices, you can also create vectors using NumPy. So let's have a look at this vector and define it as a list and use it as an input argument to NumPy array. This then gives me a vector, and its dimension is then a one-dimensional tuple. So this has only one entry, and this indicates that first of all it's one-dimensional, and the number then indicates how many entries it has. So this would be a 4-element vector. Similarly, we can also create a 3D array. For that, the nested list becomes a bit more complicated. We now need to start one level for the grids and then one level for the rows, and then we can specify an individual column. Let's have, an individual row. Let's have 2 rows, and then close the layer, so to say, or the grid, and then start a new grid and add some rows in the second grid. And just for completeness, also add a third grid to the matrix. So if we would call my3D and ask for its shape, the result of this should be a 3-dimensional tuple because it has 3 dimensions. So this would say that this is a thing composed of 3 layers, and in each layer we have 2 rows, and each row has 3 columns or 3 elements in it. You can also print this, and Python then gives us a nice output, or a nice overview of this on the console. Okay, you will rarely need 3-dimensional arrays in data analysis, I just wanted to let you know that they exist and that with NumPy you can, in principle, also go into higher dimensions like 3, 4, 5-dimensional objects. We today, however, will only need 2-dimensional matrices. We can not only access the shape of the matrix to get its dimensions, we can also access another attribute, which is called dtype. And this then tells us a bit about the data type of the elements in the matrix. And since we defined our nested lists, which we gave as an input into Numpy Array as a list of float variables, the data type of the matrix is also float64. So for all our purposes, float64 will be equivalent to Python's float data type. And if you in turn define an array which only consists of integers, then the data type of this would be int32. So once again, for all our purposes, int32 will be equivalent to the int data type from Python. If we ask for the data type of the arrays themselves, I'm sorry, they are NumPy arrays. So a NumPy array is a very general structure which can have an arbitrary number of dimensions and which can have arbitrary extent into each dimension. Here we were defining our coordinates as a 4x2 matrix. Okay, so next topic is indexing. What if we want to have a look at certain elements from the array? How do we do this? So first, let's print it again to see how it looks. And then let's say we want to grab the second element in the fourth row, second column. We would then type coordinates, and we can use the very same way of indexing that we already know from lists. So using square brackets, and then using whole numbers as indices, where counting, please keep that in mind, starts at 0. So if we would type 3, 1, remember that the conventions is rows first, columns second, then this would give us the fourth row, second column. So the result of this should be 5, which in fact it is. It also works to use slices on the as indices. So if, for example, we say column 2 again, and for the rows, start from the second last element until the end. This is a slice which would say, give me everything from the second last element until the end. And the result of this should be the numbers 4 and 5, which is also correct. These are then returned as a separate array. Often one wants to extract entire rows or entire columns. This also works. In this case, the slice index only has to be replaced by a pure colon. So this would say, give me the first column and give me everything from this first column. So the result of this should be another array containing the numbers from the first column here. Okay, so now that we know this, adding values to entire columns or entire rows for which we needed a for loop when we were working with nested rows should be easy. So for example, we can write coordinates first column is equal to coordinates first column plus 1. And if we would then print the coordinates again, they would have changed in the sense that we have added 1 to each value in the first column. Note that this kind of row and column operations are not possible with our nested list, because indices of this kind do not work with lists. With lists, we can only index the outer level or the inner level at the same time, but we cannot index both. Now, there's another way of indexing, not based on whole numbers or integer numbers, but based on true-false values. This is called Boolean indexing. And the idea behind this is to pick out all the entries that meet a certain condition. If, for example, we take our coordinates and say coordinates greater than or equal to 10, this is a logical statement which can be true or false for each entry in the array of coordinates, or in the matrix of coordinates. So if we run this, we, as an output, get a Boolean matrix or a Boolean array, which has the same dimensions as the original array, but now contains true where the condition is true and false where the condition is false. Now, the great thing about this is that this can be used to just grab all the elements which fulfill this condition. So once again, we're calling the coordinates matrix and we are using square brackets, indicating that we are indexing. And we are simply indexing with this condition now. And we say all the values meeting this condition should be set to 0. So if we have a look at the true-false matrix, this would mean that the third and fourth entry in the first column would become 0. Let's see whether this worked. Great. So this is Boolean indexing. The Boolean array can also be used to not just filter out entries, but also to modify selected entries. Okay, the next topic is broadcasting. Broadcasting means to match the dimensions of arrays, if that is possible, to perform certain operations. So here's an example. We still have our original coordinates. And let's define a row vector as a Numpy array containing only the values 1 and 2. Let's look at this row vector. Okay, so in principle, this row vector can be added to each row of the coordinates, but it does not immediately work because the coordinates have different dimensions than the row vector. Now it turns out that NumPy automatically takes care of this. So if we ask NumPy to calculate the coordinate matrix plus the row vector, NumPy takes the row vector and replicates it over all the rows of the coordinate matrix before adding it to this coordinate matrix. This is possible because the number of entries in the row vector is equal to the number of columns in the coordinate matrix. So in this way, we can also change the coordinate matrix by writing this back into its variable name. Let's now say we define a column vector which is also a Numpy array. And in order to enforce a column vector, we need a two-dimensional nested list. That is, we have to put all the numbers in single lists being contained in a larger list. Let's have a look at the column vector and also access its shape. Okay, this time the vector is not column compatible, but row compatible with the coordinate matrix in the sense that it has the same number of rows than the coordinate matrix. So once again, adding this column vector to the coordinate matrix works because the column vector is replicated over all the columns of the coordinate matrix before performing the desired mathematical operation. By the way, this does not only work for addition, but also works for multiplication. So if I instead multiply the coordinate matrix with the column vector, I get the first column multiplied with the vectors of the column, with the values of the column vector. Okay, so this is referred to as broadcasting, matching the dimensions of the arrays in order to perform certain operations. Note that this only works if it is, or that this only happens if it is technically possible. For example, if we take the coordinate matrix and not add a 2-element row vector, but a 3-element row vector, we get an error saying that the operands could not be broadcast together because they have incompatible shapes. So if the shapes of the arrays are not compatible, no broadcasting happens. It also protects the user or the programmer from unpredictable sort of things happening. Okay, so finally, matrix multiplication. How does matrix multiplication work in Numpy? Let's get back to the example, which I also showed you on the slides, and try to work out this matrix multiplication using Numpy in order to check our result and check that we're actually doing the right thing. So we define a first matrix as a Numpy array, and we need a nested list in order to define the two-dimensional matrix. And we take exactly the same list of coordinates that we were using before, closing the outer list. So this is A, and then we also define B. Once again, a nested list. This time it's a 2-by-2 matrix, meaning that the outer list has 2 entries for 2 rows, and all the inner lists also have 2 elements for 2 columns. Okay, it's always a good idea to check what you did by just printing its output to the console. These matrices look okay. And then NumPy contains a function which is called matmul for matrix multiplication. So calling matmul with 2 input arguments will multiply these 2 matrices. And the result is our matrix containing the numbers 7, 10, and so on. So the result is correct. So we are almost there to write a function which is required by our objective. There are just 2 things that we still need, namely 1, conversion from degree to radians, because we want our function to accept angles in degrees. And then the sine and the cosine functions. Now, these things are pretty basic, so they should be contained in the math module from Python's standard library. Sorry. So my suggestion now is to import Mars and then dir Mars to see what's inside and have a look where the relevant functions are in this module. Okay, so now it's time for a little exercise. Please write the desired function for coordinate rotation as given by this objective. So you may now pause the video and take yourself some time, 10 to 15 minutes, to write the function and then return back to the video. Okay, here's the result for this little exercise. I have a Python file named coordinates. This is a module. It contains a single function. And this function is called rotate. Okay, what is this function doing? First, it converts the angle, which is an input argument of the rotate function, into radians using a built-in function from the Mars module. And then second, it creates a Numpy array where we take this angle theta and submit it to the sine and cosine function and use this to create the two-dimensional rotation matrix. The 2x2 rotation matrix is then used together with the coordinate matrix as input to the function matmul from NumPy, and this returns the matrix product of these two matrices, which, as we know from earlier, is the set of rotated coordinates. So this could also be done different. You could first write this into another variable, let's say rotated coordinates, and then only return the rotated coordinates at the end of the function. Yeah, so this would be an equivalent solution. So in order to write this function, we needed two things that we had to import, which are the Mars module from the standard library and the NumPy package, which is a third-party package, but contained in your Python distribution if you're using Anaconda, for example. Okay, now in addition to this, I have written a little script, which is called rotation. And this script is now using the rotate function from the coordinates module in order to fulfill our objective. So we are importing the coordinates module. And we define some coordinates. I define them to be exactly equal to the ones which we also used in the session so far. And then I calculate rotated coordinates as coordinates.rotate, so using the function rotate from the coordinates module, and gave as an input our matrix of coordinates and an angle of 45 degrees. So what I'm also showing you, or more precisely what I'm giving you a glimpse at with this script is basic plotting functionality in Python. So I've here imported another library, matplotlib, and from this library, the submodule pyplot. Pyplot contains function for creating a scatter plot, and as input arguments, you only need to supply the x values and the y values, which in this case are just the first and second column from the coordinate matrix. Same for the rotated columns, and then we should have two sets of plots, or two sets of points on our figure. And finally, we show the function. We are showing the figure, I'm sorry. So if I run this, I get an output. Let me please undock this so that it's more clearly visible. So this is the function where here in blue we have the original coordinates, and in orange we have the rotated version of this coordinates. There's a lot of other things which you can do with matplotlib. You can modify colors and marker size and all those things. Here I'm just showing you two things, namely adding a vertical line and adding a horizontal line, which will work in the figure as our axes, x and y axis. So the y-axis is, of course, a vertical line located at x equal to 0, and the x-axis is, of course, a horizontal line located at y equal to 0. And if I run this again, I get a second plot. And this second plot now looks like this, which is exactly like what I showed you on the slide before. So now we have also the axes and the origin point marked by our nice black lines. Okay, one last thing that I wanted to emphasize here. We will have a closer look at matplotlib later in the session on data visualization. So please don't be scared if you don't understand this code by now. We will have a closer look at this later on. And second, I was also using aliases here in my code. Yeah. So I did not just import NumPy and import pyplot from matplotlib, but I imported them as NP and as PLT. So the reason for this is simply to make your coordinates to make your commands a bit shorter. Yeah. You just have to type a fewer number of letters if you are importing NumPy as NP, and your code becomes a bit more readable and a bit more accessible to others. So I would say that importing NumPy as NP and importing pyplot as PLT has already become an industry standard, and you will often encounter such imports when you are looking through online tutorials or when you are looking into answers to questions found on the web, for example, on Stack Exchange. Okay, so this is it for today. So this was all I wanted to tell you about array computing. Please have a look at the exercise in the online course notes. And with that, I want to say goodbye and have fun with the other videos. Bye-bye.